So in today's course, we're going to go ahead and talk about mutating algorithms. I've described them briefly to you before. They're basically algorithms that work on a range of iterators, but can change the order, change the contents, and so on of the data elements. So let me go ahead and shift over to my IDE and we'll begin the discussion. So the term mutating algorithm may give the impression that this category of algorithms always modifies the elements in a container. Of course, some mutating algorithms do this. So for instance, things like remove will remove items. Fill will, of course, make changes. Copy makes changes. But other of the algorithms that are mutating algorithms simply reorganize or rearrange the elements based on some rule. For example, the sort algorithm will rearrange the items. It doesn't actually change their values. It just rearranges how they are going to be laid out in the underlying container. As you know, all STL algorithms work with iterators. These iterators can be used with different types of containers, or in some cases, no containers at all, as is the case with the native C STL built-in arrays. So in this context, it's important to remember that the algorithms themselves don't really know whether or not they're working on containers or arrays. And so therefore, when you do operations like remove, it doesn't actually get rid of the elements in the container. It simply overwrites them and then returns a new iterator to the end of the new range that corresponds to taking the elements out of the container. And so that's why you sometimes have to do a two-step process where you use the algorithms to do some mutation to the contents, and then you have to do some other things to actually truly erase the elements from the container. So that's why you have to think carefully about how remove works. Remove also will look for values or predicates and apply those to all the elements in the range. So if you're doing things like an index-based remove, which is the case for our assignment number 4, you should be aware that you don't really want to use remove for that. There's other ways to do it that are much simpler by using copy and copying over the elements. Here's a list of some of the mutating algorithms, some of the common ones. We have looked at a lot of these. We've looked at copy. We've looked at other ones briefly like replace. We've looked at remove and so on. Now we're going to go through and look at a lot of algorithms, and we're going to break them up into little categories so you can see how they work in different ways in a very systematic approach. So there's a number of mutating algorithms that do filling, generating, and transforming operations. So algorithms like fill and fill-n, which basically give a value to every element in a range or an elements in a range. Generate, which basically creates a generator function that will be used to change the items in a range to be the values produced by the function object that's passed in, which is often, for example, a random number generator. We'll see some examples of that. Generate n, same kind of idea. Transform, which we've talked about before, which goes through one or two ranges depending on which version of transform is used, and makes calls to either binary or unary functors in order to do some transformation on the elements in that range. So we're going to take a look at transform here. This is a really fun algorithm. And in addition to talking about a couple of different variants of transform, this will also give us a chance to talk about how the iterators can be defined on various types of containers. We're going to use the simple string container in this example. And this will be helpful because your assignment number 4 uses, or you have to implement iterators for assignment number 4. And this will give you a few more tips on how to do this. We've already talked about this before, but I wanted to give you more details as we get close to the due date. So we're going to use the 4-parameter version of transform in order to take a string, in this case a simple string, that's in uppercase and convert it to be a simple string that's going to be in lowercase. So here's the main program. As you can see, we define ourselves a simple string that has hello in all caps, and we write that so we know that it's all caps. And then we call this method called lowercase, passing in the string, and that'll give us back an updated version of the original string s, which will be lowercase, as we'll see in a moment. And then we go ahead and write that out. So let's go ahead and run the code. I have a whole bunch of instrumentation here, so a lot of other things that go flying by on the screen. But the key thing I want you to see here is we print out hello, And then after we lowercase it, we print out hello. So it's been lowercased. We'll come back and see what all this other stuff is going on in a minute. That's there so you can see what's going on under the hood. So here is the lowercase algorithm. As you can see, we pass in a simple string. And right now I'm not using the move optimization, but I'll turn that on in a minute and show you the difference that makes in the output, the amount of output that's generated. And what you can see we do here is we go ahead and we start at the beginning of the string, the simple string parameter, using cBegin, which gives us back a const iterator to the beginning of the string. We then get cN, which gives us back a const iterator to the one past the end of the string. And then we're going to go ahead and transform this by applying this lambda function to every element, every character in the range from beginning to end of the string. And you can see what we do here is we're going to take in a character, which is, in this case, a char C. If the character is uppercase, we convert it to lowercase. Otherwise, we just return C. So what that does is that performs that transformation, and then we store the results back at the beginning of the string itself. So we're going to be doing basically uppercase to lowercase conversion in C2 in place. And you'll notice how we pass in stir.begin here, because this is actually going to change the contents of the simple string, as opposed to cBegin and cN, which are just used to read the contents of the simple string. And then when we're all done, we're going to go ahead and return the string parameter that we've just modified. Okay, so that's the high-level view. Let's just quickly recap for completeness what transform does. Transform, of course, is the algorithm that we're actually looking at here. That's the mutating algorithm. Everything else is there just to kind of illustrate other cool points about iterators and so on. So here is transform. As you can see, it starts at the beginning of the range, goes to the end, and then every step along the way, it calls this unary op, passing in the current item that's pointed to by the iterator. That gets stored into the current output iterator result. And then after doing that, first and result are both incremented by 1. So we just kind of iterate down the range, transforming as we go. So hopefully that makes sense. And you can see here that we pass in const iterators to the simple string parameter, and then we have the update done in place by having a non-const output iterator that's used to store the result. Okay, so that's what transform does. So going back to looking at what comes when we run the program, you can see that there's a bunch of stuff going on here. First, I want you to notice that when we create the simple string, the one that says hello in all caps, this guy, that ends up calling stir new, which makes a copy of the parameter of the hello string, and that's being called in the context of the simple string constructor that takes a const char star. And then this call here is calling the const char star conversion operator to automatically print out the contents as a const char star. And there's already an IOStream insertion operator that knows how to do that. So that's what's going on there. Then you can see down here when we pass this parameter in by value, because you can see it's a value-based parameter passing. We pass in simple string, not const ref simple string. That's going to end up calling the copy constructor to make a copy of this. So now for kicks, let's go ahead and change this to be the move operation. And let's rerun this code. And you'll see that what happens now, when we have the move optimization turned on, no longer do we have the copy constructor called here. Instead, we simply take S and we move it, and that doesn't do copying. That just basically scoops up the contents of the S parameter and then moves it into the parameter that's used here as the local parameter. It does an ownership transfer, and then we start doing the transform. So that's, of course, going to be faster. You'll also notice that at the end here, they do what's called a return value optimization call, and that's basically down here. It's essentially taking the contents of this string and moving it into S. So again, that's using the move assignment operator. So just a few things under the hood. That's not really the key focus of this. I'm just showing you once again why it's so powerful to have the move optimizations. Let's turn off the move optimization for the moment. that's not really going to figure into our discussions. And let's go ahead and take a look at the iterators, because that's the interesting part. So the iterators here, you can see we use cBegin, cEnd, and begin, and we're going to go look at simple string and see where those things are defined. So if you look at simple string, you can see we have a couple of forward declarations up here, simple string iterator and simple string const iterator. And then if you look inside of the simple string class, you can see that we define various traits. So these are all essentially traits defined to mimic the STL container model. So even though simple string is not an STL container, we're going to mimic the STL container model a little bit by defining these type defs so that simple string will have traits like value type, iterator, and const iterator. And we could use that in generic programs if we needed to. We don't actually use that here, but it's just a common thing to do. So all the code up here is stuff that we've looked at before, things like the copy constructor and the move constructor and the copy assignment operator and the move assignment operator and the destructor and so on and swap, blah, 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 blah. That's all pretty conventional. What I want to call your attention to are these methods here. And I've only implemented about a half dozen of them. I didn't go do the whole gamut and also implement all of the reverse iterator stuff. But I could have done that. It would have been very easy to do that. So what we have here is we have cBegin, which, as you can see, returns a const iterator. We have begin that returns a non-const iterator. We also have a version of begin that's designed to work with const ref or const objects, and that returns a const iterator. And then we have end that returns an iterator, end that returns a const iterator, and then we have cEnd that returns a const iterator. And so you can decide sort of which is the appropriate thing to use under the circumstances, or you can let the compiler make that decision for you, which it's very happy to do. And in fact, if you take a look at the Piazza discussion group, you'll see I put a little hint up there for your assignment 4, so you can use the copy algorithm in the copy constructor of array list by basically doing a little trick to cast away const for the purposes of that particular use case. The right way to do it, of course, is to implement the const iterator, and you're welcome to do that if you want, but it's not required. So take a look at my Piazza posting just so you'll know what's going on there. Okay, so these are the key factory methods that are defined in simple string, and I think you'll agree that we use them here in order to be able to make the appropriate and desired types of iterators. Now, if we want to see how things actually work under the hood, let's first just recap how the actual simple string is laid out. We've got these internal fields like len and stir, and that's what's being used under the hood to keep track of the elements in the string. And then we have various operations here, like we have operator subscript, which can be used to index into the string. And that's what we're going to be using for our iterator. And I'll talk about different ways of doing iterators here just to compare and contrast them. Okay, so now let's go ahead and take a look at the non-const simple string iterator. And you can see that simple string iterator, which is the non-const version, is going to inherit from the iterator class. It's part of STL. It's going to implement a bidirectional iterator. Your implementation, of course, needs to be a random access iterator, but I decided to keep my implementation lightweight just enough to do this example, and also so that you'll have to think about some of the operations on the iterator without me just giving it all away to you. And in this particular case, then I go ahead and say that this is an iterator for the simple string class. We also make simple string a friend of simple string iterator so it can access one of our private methods, which in this case is a constructor. Okay, so now we're going to go ahead and implement the various bidirectional operations required on our simple string iterator. And the first pair of them, of course, are the dereference operator that returns a reference to the item contained at the current position. So assuming that you've got yourself to the position in the simple string that you want to be referencing, and you could do that through, in our case, plus plus or minus minus, probably plus plus, then operator star will return a reference to the item. And you can see this version returns a non-const reference, so it can be used on the left-hand side of an assignment statement. And this version returns a const char ref operator star const method. It's a bit of a mouthful. And that one is one that can be used when you're accessing a const object or a const ref object where you need to use the dereference operation on the right-hand side of the assignment statement, as we would do, for example, if we were using the transform algorithm we just looked at. Remember, transform over here uses that dereference operation on the right-hand side of the assignment, which corresponds to the cbegin, the const iterator. And then the left-hand side is using the non-const iterator. So we use begin to get the non-const version. We use cbegin to get the const version. And everything will then magically work out because of C++'s type resolution rules. We also define another pair of operations that are very canonical in iterators. In fact, they're pretty much in every iterator category, and that's the operator plus plus. And you can see we have the pre-increment operator plus plus and the post-increment operator plus plus. And these are very subtly different, and they have different syntax, and the syntax is a little wonky, but you just have to get used to it because they always look like this. So this version is used when you do something like plus plus iterator. And the idea there is you want to increment the iterator and then give back an iterator to the incremented version. This version is iter plus plus. This is the so-called post-increment version. So this would be iterator plus plus. In that case, you want to get the current value, return it, and then increment the iterator by 1, because that follows the semantics of post-increment. And as you can see here, the syntax is a little bit weird. You just pass in an int. You don't actually have an int. You just have a placeholder that's syntactically used to differentiate the two methods. That's the only reason it's there. And yes, it's weird, but you just got to suck it up and deal with it. You'll also notice that the pre-increment operator plus plus returns a reference to a simple string iterator, where the post-increment operator plus plus returns an instance of simple string iterator. And that figures very prominently into the complexity of implementing this particular pair of methods. There are also equivalent versions of these methods for decrement. So we have pre-decrement, which would look like this, of course. And then we also have post-decrement, which would look like this. And same basic idea. This version here, the one that returns a simple string ref, does the decrement and then returns a reference to the decremented iterator. This version will make a copy of the existing iterator, then increment it, and then return the copy before it was incremented. So that's, or decremented. That's the pre-decrement operator. Sorry, post-decrement operator. Gets confusing. Okay. Then we also have a couple of other operations to make everything work properly. For the bidirectional semantics, we have the equality operator that checks to see whether two iterators are equal, and then we have the non-equality or inequality operator that checks to see if two iterators are different. And that's used typically in loops to decide when you're done going through a range. All right, so those are the main operations we have for the non-const version of this, and we'll look at their implementations in a second. Then down here we have a private constructor that's given a simple string ref and a size, and it goes ahead and makes the corresponding iterator that we need for that particular range, and we'll see how that works. Your assignment 4 is a slightly different in its implementation. This implementation keeps a reference to the underlying simple string and a position as an int into that range. The implementation that you will use for assignment 4 just keeps a pointer. Same basic idea. One is not better than the other. It's just they're different, and I did it this way so that I wouldn't completely give away the solution for you for assignment number 4. Down here is the simple string const iterator, and what this says is we can't make changes to the underlying simple string that we're iterating over. That's really what it means. It doesn't mean that the iterator can't advance. That's not what const iterator means. It means that through the const iterator, you can't make changes to the underlying object, the underlying container, in this case, the simple string, that's being exposed via the iterator. And really the one and only difference between const iterator and iterator, non-const iterator, is that the const iterator does not have a non-const dereference operator. So you can't use operator star on the left-hand side of an assignment statement if it's a const iterator. And just to prove that to you, if I go over here and say C begin as opposed to begin, now I've got myself a const iterator. If I try to compile this, it'll come back and yell at me and say, hey, you can't do this. You can't assign to the return value because operator star returns a const value. So the way to solve that problem is just to change C begin to begin. And now if we go ahead and run the program, you'll see that the results are as expected. It works again. Okay, so that basically is the definition of the iterator classes. So I haven't shown you the implementation of those classes, just kind of shown you what the interfaces look like. And aside from that one little change, the const iterator is basically the same as the non-const iterator in every imaginable way. Okay, now let's go over and take a look at the implementation of these various methods. And we're going to start with the factory methods. So here you can see we have our first method. This is the begin. This is the factory method that returns a non-const iterator. And you can see it returns simple string iterator. And I put a little debugging information in here. If you go and run the program and see what you can see here, you can see where we call, C begin, and then you can see where we call begin. So that's basically just showing that where these things are called. And what I do here, there's a whole bunch of different ways to do this. I decided to stick with so-called initialization or initializer syntax here. There's other ways to do it. I'll show you other ways to do it. This way of doing it is nice and simple. You simply say return an instance of simple string iterator that passes in star this, because it takes a simple string reference, pass in the object by reference, and the position of 0. And of course, that works because we're making an iterator to the beginning, and 0 is the beginning of the iterator range in a simple string. I could also do this other ways. I could also have said something like this. I could have said simple string const iterator, and then I could have gotten rid of the initializer syntax and instead replaced it with this syntax. And when I do that, you see that the CLion IDE comes back and says, hey dude, use braced initializer list instead. It's more concise. So I'll leave it like this just for fun. And I'll put a little comment here saying one way to create an iterator. And then I'll come down here and say another way to create an iterator. And I think this way is better. It's not as portable as this way, but if you have the right versions of the right compilers, it'll work just fine. Now, what you see here, this is kind of funny. For the iterator that's returned from begin, for the iterator that's returned from the const begin, so this is a different version. I probably should say that this is the const begin, and this is the one that's C begin. The implementations of all these are exactly the same. It's just that the types are treated differently, and that's going to dictate how other parts of the code, other parts of STL, for example, can work with these various objects that are returned. But the implementation is always the same. If you come down here and you take a look at the end factory methods, you can see that they also do the same kind of thing. The difference being that in this case, we're not passing in 0 as the starting point of the created iterator. Instead, we're going to create one that starts with len. And len, as you can recall, is 1 past the end of the range in the string. And so that is going to be used as the end iterator. So only when we get to the point where the iterator that we're incrementing through our loop reaches and equals end, where it's len, do we know that we've reached the end. And you'll see how that gets used when we do the equality and inequality operations for this particular class. Okay, so that's basically those are basically the factory methods to make the various kinds of iterators, begin iterators and end iterators. Your implementation will be a little different than this, but it's along the same lines. So you should now have a very good idea on how to do begin and end. Let's now come down here and take a look at the iterators that we're going to implement. So these are the operations we're going to implement. Now, keep in mind, again, your code will be just a little bit different because your implementation uses a pointer as opposed to a reference to the underlying object, in this case, simple string, and a position, an index, but same basic idea. So here's the dereference operator. This is the non-const version, and here's the const version. And you can see that they're absolutely identical. And all they do is they simply index into the reference to a simple string at whatever pos happens to be at, which starts at 0, of course. And then we return a reference to the type, which in this case is a char, which is the value type. I probably should have used value type here to be more abstract, but it's pretty clear for a simple string we're dealing with characters. So I just used the specific concrete type. You'll notice once again, as was the case with the begin and end factor methods, the code is identical, but the types are different. So this version has the same code, but it returns a non-const ref. This version has the same code. It returns a const char star or const char ref. Same difference though, absolutely the same code. And that'll give you a hint as to how to write your versions as well. Notice, by the way, so for this particular case, I have to use this syntax because I'm taking advantage of the fact that operator subscript is defined on simple string. So I don't have a pointer here. I have an actual reference to a type, an instance of the class. And so I'm obliged to use the public methods that are defined here. I could reach underneath the hood and access the pointers because I'm a friend, but that's pretty sleazy and not really a good thing to do. Okay. So now let's go ahead and take a look at the increment and decrement operations. So here we're going to have operator plus plus. This is the one that does pre-increment. And what we're going to be doing here is incrementing the position by 1 and then returning star this, which will give back a reference to a simple string iterator. So in this particular case, that's all we need. That's the semantics of pre-increment. We update the reference, we move the index ahead by 1, and then we return a reference to this particular iterator that now is going to be referencing the next element. And that's, of course, how you advance through the iterator range. Here is the post-increment version. Notice again that the kind of wonky syntax. It has an int there. Very strange choice, but we just got to live with it. You'll notice the other difference is we actually return an object here, whereas here we return a reference. And if you look at the implementation, it's also different. This is one way of creating a copy of an iterator. We use the initializer syntax to say return an instance of simple string iterator that has simple string underscore as the reference to the underlying simple string, and the current value of pos as the position. So that's going to go ahead and make a new copy of this iterator, and that's what's going to be returned. And then after we make the copy, then we increment pos by 1. So that's what post-increment means. So we're not returning the incremented iterator, we're returning a copy that's been before the incrementation. So we're going to return a copy before the incrementation, then we increment. That's why it's post-increment. So that's one way of doing things. You'll see that the pre-decrement and post-decrement operations behave the same, except that they go backwards with minus minus as opposed to going forwards with plus plus. But other than that, identical. We're going to look at some other variants of how to do this in a second when we talk about the const iterator version. Down here, we're then going to look at the equality and inequality operations. And I strongly recommend you follow this sort of a pattern. So in my particular case, I needed to check to make sure that the operator equality is being applied to the same underlying simple string. And the way I do that, as I say, is the address of my reference to the simple string equal to the address of the right-hand side's simple string? And if the answer is yes, I'm now talking about the same simple string. And then all I do is I compare whether the positions are equivalent or whether they're equal as well. And if both of those things are true for this particular implementation, then equality is going to be enacted. That's what's going to be returned. It is in fact equal. Your implementation for assignment 4 doesn't use this particular representation. It uses pointers. So in that case, you just have to check to see if the pointers are the same. It's actually much easier if you think about it. And then here's operator inequality. And I think the simplest way to do this is to call the equality operator and then simply negate the results. So if you get in the habit of always doing operator inequality in terms of negating the results of operator equality, it'll greatly simplify your code and be another good example of systematic reuse. Okay, so that's basically the non-const iterator. And of course, your implementation has more stuff. You have to implement a bunch of other operations because you're implementing a random access iterator. And I recommend you take a look at some of the links I provided you in the slides that talk about how to do those kinds of things to learn more about how to implement random access iterators. There's a few subtleties you have to be aware of when you do that. Now let's take a quick look at some other ways of implementing the post-increment and post-decrement operations, and also pre-decrement, post-decrement. So it's post-increment, post-decrement. That's what we're looking at here. And what we're going to do is to show you some other ways to do this. I like the way I did it up here with the initializer syntax, but you can also do it other ways. This is another way to do it. We make ourselves a copy of the existing iterator, const iterator. We then call operator plus plus, which is the pre-increment version, by saying plus plus open paren star this close paren. So that'll end up calling this operation. And then we return the old simple string const iterator. So that's another way to do it. And then here is yet another way to do it, where we can go ahead and make a temporary, anonymous temporary instance that passes in simple string decrements, post decrements pause, which means it will make a copy of simple string const iterator before we decrement. That's what's going to be returned. And then pause will be decremented rather, after the copy is created with the old value of pause. So again, just kind of showing you a bunch of different ways of doing this. Once again, if you ask me for my preference, I would say go with this way to do things with the initializer list because it's just a lot cleaner. So at this point, you should now have a pretty good idea of how to implement your assignment 4 iterator. And if you look here, if you take a look at the code, you can see that all these calls are what's happening under the hood with the different operations that are being done when this code here in transform is being called. And I won't walk through this stuff in gory detail, but it's pretty cool. And if you want to step through it and see what's happening, you're welcome to. You might also, just for kicks, want to have some fun instrumenting your code for your assignment in order to be able to see what it's doing under the hood in order to get a better sense of if it's working correctly. And I definitely recommend doing that if it's not working correctly. If you're failing the test, for example, that's a good time to crank up the way of printing things out. You can either use your debugger or you can use print statements, but whatever you do, don't sit around befuddled for long, but instead take a look at the code.